Hi everyone and welcome to Introduction to Neural Network. This is lecture number 5, and in this lecture we're going to talk about types of machine learning and topics related to DNN training, which include loss function and loss function optimization or minimization. By the end of the lecture, you'll be able to find out or understand all aspects related to training a DNN. So let's talk about machine learning types. There is several types. The first one, which is supervised learning, which we're going to cover in this course. In supervised learning, we have input data and output data defined. We call those labels. Those are given and can be used during the training. Example of supervised learning are the classification and regression problems. There is also unsupervised learning, where only data is given, no labels are provided. A typical case for this are the clustering problems. Sometimes we can have a semi-supervised learning, where we have some labels present and some labels are not present. There is also reinforcement learning, which is used in games like chess or in robotics to basically plan a robot route or path. In this kind of reinforcement learning, we have an agent that interacts with the world or the environment around it and make observation. And this observation is being given back to the system. And as a result, the system or the DNN will produce actions, and these actions can be either rewarded or punished. Based on this, the system will learn how to do the right behavior in action. Let's go into more details about supervised learning. The purpose of the training process is to identify the neural network parameters, which are weights and bias for each neuron, such that target activity is achieved with the highest possible accuracy. In order to do this, we need to define some labeled data that can be used to train and test the accuracy of the neural network. And after that, once the network is trained, it can be deployed and used in any product or program to perform the given task. There are many parameters that are needed to be determined during the training or for training. This includes loss function, learning rate, training optimization algorithm, and other parameters. During the training, we have a training stage, and during which we have data preparation step, which will involve preparing data in a way that can be used by the training framework. This labeled data is being provided into the training algorithm, which will start an iterative approach. In each iteration, the training algorithm will assign weights and figure out how far we are from the right target. Each time new weights are specified, those weights can be stored or saved. And the process will keep repeated until we reach a satisfactory accuracy. Now, once weights are defined, we can use them later in production or deployment by providing unlabeled data and use the output of the model as the expected or estimated result. That's why it's very important to train the model well to produce the result at the highest possible accuracy. Now let's try to formulate the training problem. And let's talk about very simple case, two-class classification problem. So we have a set of data that belong to two types of animals, cats and dogs. We can simply plot this in two-dimension feature space where each class of objects or animals exist in different zone. Those features can be defined by us, and as we discussed before, in DNN, those features can be decided by the DNN automatically. But the main issue here is that those features should be separable, so we can basically find out a limiters between both of them, or splitter. Now, in the training, our objective is to find the best splitter between the two classes in the feature space. And we start with a random splitter, which composed of a set of weights and bias. Those weights and bias represent the slope of the splitter. And in each iteration, we keep adjusting this splitter and the associated weights. And we keep repeating this until we eventually find a perfect splitting or perfect boundary between both classes. This is where we said we are done with the training. It's very important to remember, in order to reach this point, we have to have two elements. First, a loss function. This loss function describes how far we are from our target, which we call it the right splitter. We also need an optimization algorithm or loss optimization algorithm that help us move from one possibility of the splitter to another possibility. And this technique actually is very important. Both elements are necessary to reach our training targets. Once we have completed training, we can use the model with the produced weight in a deployment. Based on the quality of the training, the model should produce good or bad result accordingly. So let's formulate the steps for training. We specify a pair of input data and the expected output. We also define an error function. The easiest error function will be the mean square error function, which computes the error between our target and the actual output that was produced by the DNN. If we have a sample of more than one input, then we need to sum the error for all of these samples. With the error function defined, we initialize the neural network weights using random values, and we start feeding our samples to the neural network and find out the predicted output. Then we measure the loss function and adjust the weights as we have seen before. And with each time the weights are adjusted, we loop back and repeat steps 4 to 6 until we reach a satisfactory value of the errors. At this stage, when we are happy with the outcome, we stop the training and we save the last best weights for deployment purposes. Now let's talk a little bit more in details about the loss functions as well as the optimization algorithm. With respect to the loss function is a function that compare the target and the predicted output values. It measures how well the network is actually producing results. During the training, the objective is to minimize this loss function between the predicted and target outputs. In supervised learning, there are two main categories of loss functions. There are loss functions for regression problems and there are loss function for classification problems. For regression problems, we need to make sure that the output is close in value to our target output. So the easiest loss functions we can use are the mean square error and the mean absolute difference. While in classification problem, we care about how many of the outputs are really correct and at what probability we manage to get this output. In this case, we use a binary cross entropy or categorical cross entropy loss functions. Those are the mathematical formula for each one of those loss functions. We're not going to go into these details now. However, as we start our hands-on sessions, we're going to explain more about each one of those loss functions. With respect to the training algorithm, let's look a little bit about how this loss will be, assuming we have the weights as single dimension and we compute the error, the prediction error at each value of those weight. So we should expect to see something like this. A case where we have a minimum loss or a maximum loss. Sometimes we can have what we call it local maximum, which means it's maximum, but for the points around it only. The same for the minimum, we can have what we call it a local minimum. The training algorithm is an algorithm that try to modify the training parameter, which are the weights, such that the loss function gets smaller, and eventually, if our training algorithm is good enough, we can reach one of those minimums, either the global or the local minimum. This kind of algorithm are called optimization algorithms, and the most commonly used algorithm in our DNN training is the gradient descent algorithm. So let's explain what is the gradient descent algorithm. It's an optimization algorithm that is used to find a function minimum. This function can be anything. It can be a cost function, or in our case, it's a loss function. Gradient algorithm start with a random point in the function we're trying to find the minimum for, and keep moving in the negative direction of the loss increase. So basically, we need to calculate the loss. We need to figure out the direction of the loss increase, and then we change the parameter of our function in the opposite direction of the loss increase. That's why we call it gradient descent. And we are doing this in an iterative manner. And in each iteration, we compute again the loss function and we compute again the gradient. We can sometimes make a decision to stop searching for the minimum if we find out that our kind error is very small. So let's have an example with the function shown. This is a very simple function. In this function, we have y equal x plus 5 to the power 2. Our gradient will be dy dx, which is 2 multiplied by x plus 5. And we can select a simple initial point of x equal minus 3. In some time, it's very important also to add another factor during change of the iteration of the next value of x during the iterations, which you call the learning rate. We'll talk about the learning rate later, but at the moment we use the learning rate to find out the next potential value of x. So this is how it's being calculated. So the next value of x is the previous value of x minus the learning rate multiplied by the gradient. This minus indicates that we're moving in the opposite direction of the increase of the loss. At each stage, we compute y and stop when y increases or the difference in y changes is not significant anymore. So let's get some numbers with this example. So if you assume we started at x equal minus 3, so this get us to the point where y equal 4, dy dx, which is a gradient, equal 4 as well. And next x based in this equation will be minus 3.8, assuming our rate is 0.2. This means we are moving towards the minimum of the function in the right direction. Now, at this point, at minus 3.8 for x, we can compute the same calculation for y dy dx, and we'll end up with y equal 1.44 and dy dx 2.4, and this will bring us to a new value of x of 4.28. And if we keep doing this, we keep going towards the bottom of the hill. Eventually, we reach a minimum point that we can stop at. So in this case, we can stop at stage 6 or step 6, where the difference or the change in y is become very insignificant. It's here 0.6, 0.06. This means we can stop. However, if we'd like to move more, we can continue. We will produce less and less difference. Gradient descent, like any other optimization technique, can sometimes fail and stuck into local minimum instead of going into a global minimum. It's very crucial to pick the proper starting position. For example, if we choose this starting position, so the gradient descent will keep going from here to here to here, and it will stop at this point or close to it. However, if our starting point was in the other side of the hill, this means we can actually keep going in this direction and we can reach the global minimum eventually. Because of this, there are several variants of gradient descent that can help reduce the risk of being stuck into a local minimum, but no solution is guaranteed to achieve 100% results. In DNN, we are sometimes using another variant of gradient descent called stochastic gradient descent, which simply use subset of the input samples before making changes into the weights. We're going to cover it in more details later. This is another case when a large step could help avoid stuck into local minimum point. Assuming this is our starting point, and using a small step will get us into this inflection point where there is no change, and in this case gradient descent will stop and assume we already reach the minimum point. However, if we choose a large step, it will drive us over the inflection point and it will help us reaching a better minimum point. In order to use gradient descent for DNN training, we're going to follow the same scheme. We will define a set of parameter theta that is called training parameter. This is where our target is to optimize this training parameter. We will also need to define a loss function. This loss function will be calculated in each iteration. Gradient descent is used in this iterative manner. We calculate also the gradient of the loss function. In this figure, we have one example of 1D gradient descent. We'll use only one value for theta, but in reality, the situation could be different. These are the steps of the gradient descent. Start with initial parameter set theta 0, then compute the loss function, compute the gradient of the loss, move in the opposite direction of the loss function, and keep repeating this until we reach a minimum point. This is another example if we are talking about 2D. In 2D, situation could be difficult because we could have many up hills or down hills, and the algorithm could stuck easier. But for this example, let's see how it's going to work. We start at theta 0. Again, we compute the loss function, the gradient of the loss function, and based on this, we evaluate theta 1, which is theta 0 plus delta function multiplied by the gradient of the loss function. So now we have theta 1. We can do the same step and calculating in another iteration theta 2. And in this case, theta 2 is good enough to stop at. With respect to the learning rate of gradient descent, it's very important to pick the proper learning rate. The gradient tells us where to go, but it does not tell us how far or how fast we can go there. So choosing a learning rate, which sometimes referred to by step size, can affect actually the outcome of the search, as we're going to see. So let's see, if we have very small learning rate, we're going to move very slowly from one point to another. We could eventually reach the minimum, or we can stuck, as we have seen before. If we choose too large learning rate, we can keep toggling between minimum and the maximum point because it's going to move us quickly between the loss function. So it can move us from here to here to here to here. Then because we are moving very quickly and adding big values, big numbers, we can move very far from the minimum and we can go back and forth many times. Looking at it from different perspective, if we plot the learning rate, the loss for different learning rates against number of iterations, this is what we're going to get. If we use very low learning rate, this is going to be our curve. The loss will gradually decrease. If we use a good learning rate, it could produce better result because it will help us avoid being stuck in some of the local minimums. If you use a very high learning rate, it could push us away from the good minimums, and a high learning rate will keep bouncing across the error and it could saturate at wrong minimum. So far we talked about how the gradient descent will work, and it's very important to know that gradient descent require calculation of the gradient of the loss function. However, in DNN, we don't have a loss function or a formula for a loss function. We only have the input and the output nodes and the result of the output for a given input, which is provided by the label data as we discussed before. So the question is, how can we calculate the gradient of the loss function if we don't have a formula? The answer is we use a backpropagation algorithm to do this kind of calculation. So what is the backpropagation algorithm? The backpropagation algorithm try to figure out the change or the gradient of the errors by going backward in the network. In general, during the training phase, which we call it a forward pass, we're providing an input data through the input layer, and this data keep propagating through hidden layers until it reaches the output. We have good knowledge of what the output has been produced for a given weights, but we also have the target output. So given that we have the target output and the actual output, we can have an error using the loss function we have defined for this training. Now, what happened in backpropagation is if we already have the error at the output, we can adjust the weights that is input to the output layer. Okay. Now, those weights are also output of previous hidden layer. So we can also keep going backward and measure the error at hidden layer, which is number 3, and calculate the error at the other node, and we can keep doing this backward until we figure out the error at each node in the network. And once we have done this, we can compute the gradient of the error, and we can then use the gradient descent to adjust weights before we move into the following iteration. And this is how the backpropagation works. To summarize, most neural network use backpropagation method for calculating the gradient of the loss function. During the training, the forward pass is used to compute the weights and the output at each individual nodes. Then we use the loss function to compute the loss between the target and the produced output at the output layer. Then we backpropagate this result to the hidden nodes or the nodes in the hidden layers until we figure out the error at each weight at each node. After this, we apply the gradient descent to adjust the weights and keep repeating this operation until we reach the target accuracy or reach a low loss result. You don't have to be familiar with the backpropagation algorithm. Luckily, in most frameworks now, if not all of them, the gradient and the backpropagation is being automatically calculated by the framework itself, like PyTorch or TensorFlow. So in this lecture, it's very important to know how things are being done from high level, but you don't have to go into more details in the backpropagation algorithm behavior. So to summarize what we have covered in this lecture, we have covered the basic theory of training. We talked about the gradient descent algorithm. We talked about the loss function. We did not cover some of the training related items, like how to validate the training outcome and how to fix some of the training problems, such as overfitting or underfitting, which we're going to come to later. In the next lecture, we're going to talk about how to build and train a deep neural network using PyTorch. And also in the following lectures, we're going to talk about some popular DNN architectures.